Hello everybody. This is going to be part one of a two-part video about incircle and excircles. There's more than one excircle of a triangle. And we need to know this because we want this for the geometrical proof of Heron's formula. This is a proof that uses excircles and the incircle. And it's a lot more geometrical and less algebraic than the one I did in the last video. But also there's another reason. Everyone should know this, and especially if you are into competitions and olympiads. And also this topic is just really beautiful and really elegant geometry, and it's just wonderful, and you really should know it for that reason. Okay, so we're going to begin with some important preliminary stuff. The first thing we need is a proof that the tangent at some point is perpendicular to the radius at that point. Okay, well, what do I mean by this? Well, that's best illustrated by a figure. Here we have a circle. Let's call it C. And there's a point P, and we have a tangent line. Let's call that tangent line little t. Okay, and there is a radius OP touching the point P. Now, since T is a tangent, it only touches C at P and no other point. So any other point, for example, this point here, Q, any other point, say Q, is going to be outside C. And this is the definition of tangent. I take any point that's not P, and it's going to be outside this circle C. There's only one point that is on C, and that's P. This is just the way tangent is defined. That's the property of a tangent line. So this property is just enough to be able to prove something really interesting, that this radius here, OP, so we want to prove that OP is perpendicular to the tangent line T. And how do we do this? Well, we're going to use proof by contradiction. Yes, our friend contradiction. When you really don't know how to prove something, how to approach a problem, how to prove it, well, try contradiction. It can do some really tough things. All right, so let's think about this. Suppose that this is not true. We suppose that OP is not perpendicular to T. So if that's the case, then there exists some other point on T such that this line, let's call that point Q. So some other point on T, Q, such that okay, I'll draw in a different color, such that this is 90 degrees. So think about it. If it's not true that this is 90 degrees, let's say that is not true, then there's some other point somewhere along this line for which this is true, for which it is 90 degrees. Let's say it's this. Now, I know that it doesn't look like 90 degrees, okay? But you just use your imagination, all right? You know, it is, in fact, after all, a contradiction. It's going to turn out to be not true. That's why it looks funny. But let's assume that this is not 90 here, this is not 90, and this is 90 here. Okay, so what happens next? Such that, okay, so we choose Q such that OQ is perpendicular to T. Now, what happens here? Something really interesting happens. This triangle, O OQP. This is a 90-degree triangle. So OQP is a right triangle. And if it's a right triangle, then this here must be the hypotenuse. OP is hypotenuse. And you know that hypotenuse is the longest side of a right triangle. OP is longest side. The longest side is the one opposite the 90 degrees. So opposite the 90 degrees here, we've got the longest side, OP. But this is impossible, or it's a contradiction. Okay, so this is a contradiction. Why is it a contradiction? Well, let's think about it. Because OQ is longer than OP. OQ is bigger than OP, and that's impossible. Because OP must be bigger than OQ. So therefore, the thing that we assumed here, OP is not perpendicular to T, this is in fact false. This must be false because it leads to a contradiction. So therefore, OP is in fact perpendicular to T. This is a very, very important theorem that the radius segment is always perpendicular to the tangent at this point, at the point where they meet. Okay, this is always true, and we will always use this in geometry, and never forget this. Okay, it's a very, very useful theorem. The next thing we need is some results about the symmetry of tangents. What do I mean by this? Well, let's look at a figure. From any point X, we can draw two tangents. One is going to be at point P and another at point Q. This is always true for a circle. And what we want to prove is that this line here, this segment of the tangent, is equal to this one, QX. So let's write this down. We want to prove the following. Let's get black. Prove that PX equals QX. And we're also going to prove something about the angles too. But let's see. And we proved this by using isosceles triangles properties. Triangles. So with iso triangles, we can prove this. This is very interesting. So let's begin with a helper line like this. And we notice that, first of all, this is 90 degrees, and this is 90 degrees because of the previous proof that we did. This one, OPX, is equal to this angle here, OQX, and they're both 90 because this is radius and that's tangent, just like we proved above. So if we call this angle X, the first thing we notice is that this has got to be 90 minus X, but we can call that Y. So let's call this 90 minus X. But by iso theorem, by isosceles triangles, by iso triangle, because we have two equal sides, R and R here, this must also be X. So angle OQP must also be X. And so therefore, this must be Y. Therefore, angle PQX must be Y. So I have here also equal angles X and Y like that. Now, if you'll notice, I have a Y here and a Y here, yeah? Okay, well, we can use iso theorem again by isosceles triangles. What do we have here? Well, triangle XPQ. This triangle here from X to P to Q, this one here, this is isosceles. All right? And the two, because the two angles here are equal, so two Y angles. And so therefore, the two sides are equal. PX equals QX equals well, I don't know what they're equal to, but they're equal by isotriangle theorem. So that's very beautiful. I like that very much, very cute. And there's more. We can do a little bit more. Let's connect this here. And what do we see? Maybe I can get you to prove this, that this angle, if this angle here is alpha, then this one here is alpha by 2, and this one here is alpha by 2. It's easy to prove. Okay, prove that here, let's write that better. Prove that OX bisects angle QXP, which is equal to alpha. Now that's easy to prove, and I'll give you a hint. You've got two congruent triangles, so you just prove, but because we know that this is equal to this, then by SAS side angle, here's the angle, and side, these two triangles OQX and OPX, they have to be congruent, and therefore all the angles are the same. But I want you to draw it and, write a nice kind of a proof for it. You write a nice story like I did here with all the symbols and the writing. That's the hard part about geometry. Something might be obvious in geometry, but the hard part, the actual work, is writing it all out in a logical way like I've tried to do here. Now we get to the incircle and the excircles. So what are incircles and excircles? Well, as usual, we need a figure to help us think about that. So here I have a triangle ABC, and I've purposefully made the sides a little bit longer for a reason. Now, let's try to draw circles. Circles that touch. Circles that touch. What do I mean by touch? Touch each side of the triangle. Of triangle ABC. And what do I mean exactly by touch? I mean tangent. So they just touch at one point. They don't go, the side doesn't go through the circle. They're tangent to the side, and they touch only at one point. Now immediately we can think, okay, I can probably draw a circle inside, something like that. And yeah, that's right. That's an incircle. So we've done an incircle. That's where we get the in part of the incircle. And we think, man, there's no other way. How can I draw another circle that's touching all three sides? Well, if sides are lines, and the lines can be produced as long as you want. So if we, in fact, make these lines very, very, very long, we could create other sides which touch on the outside. So it's hard to draw here, but I'll show you in a figure coming up. But yes, something like this. All right, that's an awful freehand rendition, but it's a piece of an excircle. So here was my incircle, and here is my excircle. And I can do that here, out here. I can do that out here, and I can do that out here. Okay, and each one of these will touch all three sides. This one is touching here, here somewhere, and somewhere up there somewhere. See? It just touches externally, whereas the incircle touches internally, here, here, and here, three sides. So the best thing is to show you a nice illustration of this done with some really good software and not freehand, and you'll see how it looks. There you go. We have all our incircles and all of our excircles. So our triangle, let's look at the whole thing. Triangle ABC, the vertices are ABC, and you notice the labeling conventions. A is matched with little a. Okay. On the opposite side, here's little a. Let's use color. Here's A matched with little a. And also, A is matched with the IA in X circle. So we go in the same direction, and it's matched to the excircle, which is centered on IA. The incircle has a center at I. The excircles have centers at IA, IB, IC, and they all follow the same convention. Vertex B matches with, let's use a different color. Let's try this. Okay. Vertex B matches with side B, and that matches with IB. Vertex B, side B, IB, and then finally vertex B, side C, IC. Now, this convention here, like I say here, this convention makes proofs much easier to follow, okay? That is no understatement. It's much, much easier to follow. And if you don't follow this convention, then all of your work, it's going to become like a soup of unrelated symbols, and it will be very difficult to see what's going on in such a proof that does not follow this very logical convention here. So always label things as I've shown you up here. So again, we have our red incircle in the middle here, and we have the 3 exterior excircles, and look carefully, they are tangent on all 3 sides. This is tangent to side C here, tangent here to side B, right about here, tangent here to side A. Side C, this is side C, this is side B, this is side A. You just have to get used to following along, and it makes perfect sense. Okay, so now that we know about incircles and excircles, in the next couple of steps, I'm going to prove a few very important things about the incircle. Now let's look at the triangle and its incircle a little bit more carefully, along with its tangents. So here I have my triangle ABC. Why am I blue? Okay, I'm going to change back to black. And I have my incircle centered on I, and I have 3 tangent points, and I'm using a labeling scheme similar to the classic one. Okay, TA is the tangent point associated with vertex A, and so on, like that. And what we see here is that we have these segments. We have this one here, and then we have another segment here. These are tangent line segments, so from C to TB and so on. And we have some segments here and some segment here. Then we can do more here and here, like that. Okay, basically 6 pieces. And we want to calculate the lengths of these segments. All right, so how do we do that? Well, we can, in fact, calculate the lengths of all the segments of the tangents. Well, that's the triangle itself, but its tangents are on this circle. So the job here is to find all of these segments. And we're going to find it in terms of the known sides, A, B, C, and also the semi-perimeter. So P is going to be A plus B plus C over 2. All right. And we're going to solve for all of these segments using only these things. Okay, let's start at A, and we can start adding up these segments. So A to TB plus TB, so that's here, and then TB down to C, okay, and keep going. We're going to go around now to the next one, plus CTA plus TAB, there, we're over here now, plus TAB plus BTC, so now we're here, and then finally plus TCA. Well, this has to be the one perimeter, and that's 2P because P is the semi-perimeter. But a lot of these things are the same. So let's look at this because, okay, from what we proved before, okay, by symmetry, okay, I think that was part 2, step 2. We proved that the triangle, this triangle, well, these parts of the triangle, they're actually tangent lines touching the circle here and here. So these parts of the triangle are actually equal. These lines, and also these must be equal here, here, and here. And also these two must be equal because of the theorem that we proved in the early steps about symmetry of tangents. Now you see why we had to prove those things. So in fact, ATB is equal to TCA. Okay, TCA, this is the same thing. This one here is equal to this one here. So those two are the same. Let's use a different color now. TBC, where is that? TB to C, that's the same thing as CTA. So CTA, those two are the same. And finally, let's use a different color. TAB, that's this one. That's equal to this one here from BTC. So TAB here like that. So they all pair up. And in fact, we can now write it like this. 2 times ATB plus 2 times TBC plus 2 times TAB, yes, like that. And this is equal to 2P. And the 2's all cancel out, so now you see another reason why we use semi-perimeter and not perimeter. AB, let's write it over here. ATB plus TBC is plus TAB is equal to P. Very, very good. However, if you notice here, this combination, that's this segment plus this segment. So that's side B. And we have TCB here plus TCB here equals P. And so therefore, I've proved that this segment here, TCB, is equal to P minus B. Okay, let me erase some of this stuff. We don't need all this clutter. And let's start a different kind of clutter now. Okay, so TC to B. Okay, where's TC to B? That's over here. So TC to B, that's P minus B. Okay, we found that. And also we immediately know this one is P minus B also. Okay, because they are equal by the previous theorem that we have proved above. Now, as an exercise, I want you to prove the others, or rather find them. Okay, you figure this out. And the pattern to this is very beautiful. This is A, this is going to be P minus A. Over here, this is P minus A. They're equal. And this has got to be P minus C. This is P minus C over here. Those two are equal by the tangent symmetry theorem. So it's very, very beautiful. Okay, and you can let's do an experiment here, a very pretty experiment here. What happens when we add these two here? So we have P minus A plus P minus C. So we get 2P minus minus A minus C, and that's A plus B plus C. That's 2P minus A minus C, and that's B. Is that true? Yes, this is B, the side B. This plus this is side B, and it works. So very amazing. We're able to compute all of these segments of the tangents to the incircle in terms of ABC and the semi-perimeter. This is a very, very beautiful result, and everyone should know this simply because of the sheer beauty of this geometrical masterpiece, man. It's just so nice. Okay, we have one more thing to do to close off this part about incircle and excircle. And now let's deduce a very pretty result about the area of a triangle and its incircle. we've got this massive thunderstorm coming my way. So if you hear some funny sounds, now you know what it is. All right, so let's begin with this figure. Like the others, it's always good to start with a figure. We have our incircle, and we now draw some radii to the tangent points, the points of tangency that touch each side. And if I do that, well, now I can have these triangles inside these little sub-triangles like this. Okay, so I have one sub-triangle. Let's study this one, triangle IBA. That's IBA. And because of the theorem, remember the theorem that radius is perpendicular to tangent. Remember this theorem. Radius is perpendicular to tangent. That means r is actually the height of this triangle. And so then it's easy to calculate the area of this. Area of IBA is just 1/2 the height times the base. What is the base? The base here is C. Likewise, let's do the next triangle. I'll use yellow for this one. This one here, we can calculate its area the same way. Okay, IAC. Okay, IAC, and height is R, so 1/2 R, times the base is B. And one more triangle, IBC. Let's color this one. Give it a different color here. Sort of like purple, but not really. Okay, so that's IBC, and that's 1/2 R, and the base in this case is A. Right, so I can now compute the triangle ABC area in terms of all this by just adding all this stuff up. That's IBA area plus IAC area plus IBC area, and that's equal to 1/2. Let's factor out the R, and it's C plus B plus A. And in terms of the semi-perimeter, that's RP. And so we have this incredible formula. It's just like incredibly beautiful. Area of ABC is RP. And we need this formula if we want to continue with Heron's proof, like a more geometrical kind of version of Heron's proof. So we need this. And besides, this is a really beautiful proof. I think I've done it before in a video, but I never get tired of doing this proof, and I never get tired of showing people this proof because it's just so pretty. It's so beautiful. Okay, and so I think that when you learn this proof and memorize it, you will also get that feeling that you want to show it to everyone that you meet. So as always, if you like this video, or if you didn't like this video, just click like anyway, subscribe, and leave a comment. Tell me how you're feeling. If there are any thunderstorms in your area, let me know. And next video will be part 2 of this, where I talk about excircles, and I prove some similar things for excircles. It was just too long to do all of this into one video. And then I think we'll be ready for a beautiful proof of Heron's theorem that I'm sure many of you have never seen before. So I will see you next time.